Over the last 2 weeks of lectures, we've developed an understanding of atomic structure. We've used the atomic structure and the wave functions for describing electrons in an atom and given quantum states to describe then how transitions can occur within an atom or from a bound atom to a free electron state. And we've brought all of that together to develop oscillator strengths, which help us to understand the probability of transitions. Now, how do we put that all back together into what we've learned about radiative transfer so far? So remember that radiative transfer is a process that we have defined all of our equations as functions of frequency. So when we've talked about the equation of radiative transfer, we've talked about the equation in terms of frequency. We've said that, for example, the change in specific intensity with optical depth, nu, and all these sub-nus is equal to I nu plus S nu minus I nu plus S nu. And we've talked about also the absorption coefficient for particular species. So the absorption coefficient for a species is just the absorption, the sum over all electrons in the J greater than I energy state, so the energy state which is greater than I, the number density of electrons, or the number density of atoms with an electron in the ith energy level, times, say, the cross section for a bound transition from the I to the jth energy level, plus the number density of the atoms with electrons in the ith energy state times their cross section for actually being bound free. And we can integrate this over all of the different energy levels for an entire system. So this is what happens in this equation. And this describes the absorption coefficient for the entire atomic species, where we're considering what could happen over just transitions if a radiation field comes in, how that can produce transitions between energy levels inside that atom or from the atom to a completely free state. Now, and I'll just write down that Ni is the number density of ith energy level. So this absorption coefficient, though, is a function of frequency. It may produce something at one frequency. There may be a non-zero absorption coefficient at one frequency, and then it may be zero at another frequency, because it is quantized by the energy levels inside our atom. And that means that when we work through the radiative transfer equation, the absorption coefficient has varying values at different frequencies throughout. And if we were to write this down, draw this out, we could draw out a diagram for, say, log of frequency times the log of the absorption coefficient. And it might look for a given species something like this. It'd be decaying, declining, jumps, declines, bound free edges. So that's where we photoionize the gas, then dropping down, and various bound states. And so on. So each one of these situations here is a bound transition where the absorption coefficient is at a quantized level. And these larger slopes are dropping in as we have a drop in energy, the difference in energy between a particular radiation field that's incoming. It's going to take less and less energy to photoionize. And then these bound free transitions are the bound free edges where you jump from being, say, the ith energy level to free to the jth energy level to free, and that adjusts there. So if we allow tau to be small, such that e to the minus tau is on the order of 1 minus tau, this is a familiar situation for us, then we can write through the solution to the radiative transfer equation as I nu the incident radiation plus the absorption optical depth times the source function. This is just the standard solution to the radiative transfer equation for small optical depths. And from that, you can see straight away that if the source function, which is what our gas is, our atomic gas with its various lines, is greater than the incident radiation, then we have emission. And if instead the source function, which is our gas itself, is less than the incident radiation, then we have the natural situation of absorption. And so depending upon what frequency we're looking at, the absorption coefficient may have sent it into a state of absorbing gas, or instead in terms of it producing an emission. And so you might get plots that would look something like this. This was log nu, and this might be our intensity. And you may have a black body curve with absorption. Or alternatively, you could have a black body curve with emission. Oh, that didn't draw very well. And that would be an emission curve there. Or at different frequencies, we may have emission and absorption depending upon the different species of gas. And so this is exactly what we see when we look at sometimes at spectra from quasars, which are producing very strong amounts of emission. We might have a function which looks like this with emission lines on top of some broadband spectrum, and then also some absorption lines. And those are related to what the different gas species are and their different oscillator strengths that determine whether or not they are in emission or absorption. So you're now prepared with all of the knowledge that you've got about radiative transfer, as well as the atomic emission and absorption processes, to solve the problems that allow you to put together gas in front of continuum emission, to put together gas sitting as part of continuum emission, or gas radiating simply of its own accord via a free-free process, a bound-bound process, or a bound-free process. And from there, we'll stop our atomic species talks.